Good morning, everybody. Nice to see you, I guess. It's nice to be able to be here to talk to you about these physical concepts. Oh, wait, that's the wrong slide. Let's go back one. Okay, sorry. There we go. That's the correct slide. Conservation of energy. This is our lesson for today. Lesson number 4. Unit 3. So this is our energy unit, and we're talking about now lesson number 4. Lesson number 3 was mechanical energy. You can go back to the video there. But now we're talking about how energy transforms and the fundamental law about energy transformations. And it's a one of the possibly the most fundamental law in all of physics, that energy cannot be created or destroyed. It can only change forms. We call this the first law of thermodynamics. Okay, so the first law of thermodynamics states energy cannot be created or destroyed. Very similar to another conservation law. You would have seen it in grade 9 or grade 10. This is the conservation of mass. In chemical reactions, we have to account for all the mass that we start with on the reactant side and all the mass on the product side. In energy, it's the exact same thing. And it basically allows us to quantify physical processes. Any physical process can now be basically an accounting problem. We can talk about the energy that we start with, and going over to the energy that we can finish with. And those have to be the same. It can be changed forms, it can go through any types of different forms, but we have to account for it all. We cannot do any sort of magic. Physics has to have an accounting of energy that we start with to the energy that we finish with. And that's the fundamental law of thermodynamics, the first law of thermodynamics. We're going to talk about the other laws in the next lesson, but at this point, let's only worry about this one. Okay? So let's try this problem. Let's say we have a skateboarder. He's traveling 4.2 meters a second at the top of a 5.6 meter ramp. What is the speed at the bottom of the ramp? And now, from what you guys have learned in dynamics, you would think about, okay, so what's the shape of the ramp? How do we calculate its acceleration and then its velocities and all that sort of stuff from a dynamical point of view? And then that process is what we call a path-dependent process. It worries about the shape of the ramp and all kinds of stuff, like how far it had to go in the X direction, the Y direction, and it's a very complicated process. But now that we have an understanding of energy, it becomes a very simple state-based problem. And what I mean by state-based is that we only care about the initial setting and the final setting. And we only look about it at what energy we started with and what energy we end with. But we can state, using our new conservation law, right, all we have to say here to solve this is that the energy that I start out with, let's call this EI, okay? That's my initial energy to begin with of the skateboarder before he's gone down the ramp, is going to have to be equal to his final energy. Sorry, their final energy at the end of their ride down the ramp. Could be even a loop. Who cares about the shape? The shape means nothing. It can be a loop. As long as it has enough kinetic energy to go around the loop, it could even be a loop. It doesn't matter. All that matters is we know its initial conditions and its final conditions. Anything that happens in between doesn't matter. This is a path-independent problem. Okay? It is state-based. It only cares about my initial state and my final state. So let's think about the first state. He's traveling at 4.2 meters a second. What kind of energy does he have? Kinetic, okay? So he has some sort of initial kinetic energy. Okay, let's call this Ki. He's also 5.6 meters above the ground. And if we're going to use the ground as our reference point, that means he's going to have some sort of initial potential energy, and we call that a U. Okay, so he's going to have a potential energy to begin with. And at the bottom of the ramp, because he's finally hit the bottom of the ramp, there is no energy in terms of potential. He only has a final kinetic energy. We could put plus UF, but that's just going to be 0. Why don't we just do that? Let's just plus is final, right? But because our reference point is the ground, this is just going to be 0. So we're not going to care about that. All right. So another question you might have had is, how heavy is the guy? Don't we have to know how heavy he is? Don't we have to know what his mass is, so that we can look at, from a force point of view, force is equal to mass times acceleration, and we get some sort of gravitational force. Where's the mass? They didn't give us. Did they give us enough information? Uh-oh. Let's just keep going though. Okay, from now let's go back here. So I have half mv squared. So half. Oh, that's an m. That's not a 2. Half the mass of the skateboarder, initial velocity of the skateboarder, squared. So that's his kinetic energy, plus mass times gravity times his height, which is his potential energy, is going to be equal to half the mass times his final velocity squared. Okay, so this is going to be his initial kinetic energy, his initial potential energy, and that's the sum of those two energies. His total mechanical energy is going to be equal to the mechanical energy at the end. And now what do we notice about the m's? I can factor an m and have another m here. So wonderfully, my m's, they cancel out. It's independent of mass. It doesn't care how much the skateboarder weighs. It doesn't care about the mass of the skateboarder. It doesn't matter in the question. They cancel out. That's beautiful. Anyways, also I can multiply everything by 2. If I multiply everything by 2, the halves cancel. So let's rewrite this as initial velocity squared plus 2 times gh is equal to the final velocity squared. Okay, so all the halves have been removed by multiplying everything by 2, and the m's have canceled out. Remember, it's asking me for the speed at the bottom, which is Vf. It's still squared, so why don't we write this, that the final velocity is going to be equal to the initial velocity squared plus 2 times g times h and square rooted. Okay, and look at that equation. Does that not look familiar? Does that not look familiar? Remember, if we look back at our kinematics equations, back to our initial kinetic, way back, we have this equation that v2 squared is equal to v1 squared plus 2a delta d. Right, and look at this, v2 squared is equal to v1 squared plus 2g, the acceleration, and its displacement, we called it h, height. Exact same expression, but instead of coming up from a kinematic point of view, we started off at a completely different idea. We started off from a conceptually completely different idea that energy has to be conserved. This has nothing to do about graphs of areas under velocity time graphs or any of that nonsense. This is a purely energy state dependent analysis, and it ended up with the exact same equation. That's beautiful. But anyways, moving on. So let's see. Let's go here. Let's do the actual math. V1 squared, that's going to be 4.2 meters per second, all squared, plus 2 times 9.81 meters per second squared, multiplied by 5.6 meters, and then the whole kit and caboodle is going to be to the power of a half. Power of a half, same thing as square root. So what are we going to get? 4.2 squared plus 2 times 9.8 times 5.6. And then we're going to square root the whole. Square root, do it. Square root of everything. So that's going to be a final velocity at the bottom of 11.3 meters per second. Okay, so we ended up with a final velocity. This is the skateboarder's speed when he gets to the bottom of the ramp. Okay, started off at 4. Wow, wait a second. That's about 40 kilometers an hour. Don't go down 5.6 meter skateboard ramps. That's a lot. What's that? That's like 16 feet. Ooh, okay. Yeah, because by the time you get to the bottom, you're going to be traveling like 40 kilometers an hour. All right. Okay, so moving on. Next question. Okay, so using this analysis, it says that His speed will be about 11.3 meters a second. Really, that should be 11. Using proper significant digits, let's just go with 11 meters per second. Notice that I'm not using this as a vector, I just kept it as a scalar. Keep things simple. Notice there's no problem with vector, no problem with x's and y's. It's only energy. It doesn't depend on the path. It's not a geometric problem. The question is, why wouldn't it actually be the speed? Why would his speed have to be different? Where energy cannot be created or destroyed. So our initial expression here, I equals F, that is true. That's the first law of thermodynamics. Okay? That cannot be wrong. However, our expression there that the kinetic plus is equal to the final kinetic, that one was actually wrong. Why was that wrong? What are we missing in that second line? We're missing all the extra heat. And I'm calling this heat, but really I'm talking about everything. This is talking about friction in the bearings. Well, it's bouncing a little bit. So that's the friction in the bearings. That's the air resistance. Anything else like that. Anywhere else that we would have lost energy. The second law of thermodynamics, actually, what we're going to talk about in the next lesson, states that that it's impossible to have this happen without some loss of energy. Okay, we call this entropy, okay, randomness. Excuse me. So we call this entropy or randomness. Whenever these things happen, any transformation, any sort of process from initial to final, there always has to be some energy lost to the system. Okay, and that's called the second law of thermodynamics. So this means that because there's going to be some energy lost to friction, to air resistance, to everything else, his velocity actual is going to have to be less than his theoretical from our initial problem. He's going to be traveling slower. Okay? And that makes sense, right? As he goes down the hill, he's going to be doing some of his motion that he's traveling down with is going to be doing other things other than transforming potential into kinetic energy. He's going to actually be losing some energy to other things, right? Like having to move the air out of the way. The faster you travel, the more difficult it is to move the air out of the way, the more inertia there is from that air. Right? You feel that. Right? If you move your hand slowly, you don't feel the air, but if you move your hand quickly, you feel more resistance. You stick your hand out of a car, you can feel all the air trying to get out of the way. And you're doing work on that. You're pushing the air out of the way. You're increasing the kinetic energy of the air. And for you to increase the kinetic energy of the air, you have to lose some of your kinetic energy. All right. So this is a little bit farther into what we're going to talk about in the next unit. Okay. So there's always going to be some loss. When we say loss, whoops. This is a loss to the system. We can talk about that a little bit more. This is the second law of thermodynamics. Let's try another one. So, cannon fires a 3 kilogram cannonball at 250 meters a second off of a cliff. When the cannonball hits the ground, it's traveling 300 meters a second. Determine the height of the cliff. Let's draw a quick little picture. Here's my cliff. Incoming Mr. Stone diagram. All right, so cannon. Wow, beautiful. And it's gonna fire a cannonball. Off it goes, and it's gonna hit the ground. All right, so it has an initial velocity. Let's call it VI, and it has a final velocity VF. Okay, what is the height of the cliff? What is H? What is this height here? You don't know what that is. So let's just go back to our simple expression of energy. Initial energy is equal to final energy. Initially, it has some kinetic energy from the chemical energy released in the gunpowder. And it has a potential energy because it's some height above the ground. Right, we're going to use this as my reference point. We're going to use the ground as my reference point for 0 potential energy. And so then in the end, it'll only have its kinetic energy, right? So again, replacing everything. 1/2 mass of the cannonball, its initial velocity squared, mass of the cannonball, GH, is equal to 1/2 mvf squared. Okay? And again, let's cancel out the m's, so that 3 kilograms really doesn't matter. Multiply everything by 2, again, to get rid of the fractions. We end up with v1 squared, or vi squared, plus 2gh is equal to vf squared. And solving for h, we're going to get, this is vf, that should be an I, vf squared, take away vi squared, all over 2g. Okay? All right. So that gives us an expression for the height. I can plug in all my numbers, and what am I going to get? That's 300 squared. Take away 250 squared, divided by 2 times, where did that g go? 2 times 9.81. And we end up with a height of, holy cow, 1.4 times 10 to the 3 meters. It's a 1.4 kilometer high cliff. Okay? So, again, same idea. We have an initial mechanical energy that has to be equal to the final kinetic energy. Okay? So, again, we're just using energy conservation, and we end up with an expression that tells us its height for that energy conservation idea. Okay? This one, we can do that. We can skip that. We can do quickly. Kinetic energy at the top, we have the speed we can calculate. This is basically the same problem we've just done twice here. Okay? All right, so why don't you try these problems here? There's 4. Almost the same idea. We're given energy, and we have an initial and a final kinetic energy. Remember, that's all these problems are going to start with this expression. Right? The initial energy is equal to the final energy. And from there, we can calculate everything. All right, so try those problems for homework, and good luck, and stay safe out there. Okay, and hopefully these lectures are keeping you sane, because I know they're keeping me sane with my 4 kids and everything. So best of luck, and I'll talk to you later.